So in this video, we're going to start talking about solving exponential equations. So this is exactly what it sounds like. It's going to be equations which involve exponents, particularly where we have a variable in the exponent. Okay, so it'll be different from where in polynomials we had exponents, but they were numbers. Right here, the variable is actually going to be in the exponent. So let's start with a simple one to get us started. So let's say that we have 2 to the x minus 1 equals 2 to the 2x minus 4. Okay, so there's a couple of different ways we can approach this. Probably the simplest way to think about all of these really is going to be using logarithms and using the logarithm properties in order to simplify these. Okay, so as we've seen, anytime we come across an equation, we can do basically whatever we want to both sides of an equation, as long as we do it to both sides, right? That will still preserve that equality. So what could we do to both sides of this equation in order to simplify this? Well, what happens here if we take the log base 2 of both sides? Okay, so let's say we have log base 2 of 2 to the x minus 1 equals log base 2 of 2 to the 2x minus 4. Okay. So why would we do that? Well, first of all, with the log properties, what this allows us to do is that we can now pull that exponent down out of the exponent space, right? So we can turn that exponent into a product. So that's a big advantage that we have now with logs, is that it's going to make dealing with exponents a lot more simple. So doing that here, this will leave us with x minus 1 log base 2 of 2 equals 2x minus 4 times log base 2 of 2. And now this should make it clear why we chose log base 2, right? So we could have taken any log of both sides, and it would still preserve that equality. But the reason we chose log base 2 specifically is that log base 2 of 2 is equal to 1. Okay, so I chose the same base as for the logarithm as the base of the exponent here. Okay, so because this is just 1 and this is just 1, this just becomes x minus 1 equals 2x minus 4, right? So then it's just a normal equation that we can solve pretty easily. Okay, so this is a new type of equation, so we should think about, are there any like catches here? Namely, the thing we might run into is like a domain issue, right? Sometimes the things we get in our answer, they don't line up well with the domain of the function. So in this case, there's no domain issues with exponential equations. There will be when we get to logarithm equations though, right? We do have to think about the domain of logarithms, but here with an exponential equation, or specifically just with an exponential function, the domain is all real numbers. So there's no reason to worry about the answer here, right? If we plug this in, we're not going to have any domain issues on either side. Another thing that maybe we should question is, when we take the log of both sides, we do have to be a little bit careful about that, again, because of the domain issues. In particular, we saw that we can't take the logarithm of 0 or a negative number. So if we're taking the log of both sides of something, that equality is only preserved as long as we're not running into any of those domain issues. So luckily here, we don't have any of those issues because this is an exponential function. And the exponential function, the range is 0 to infinity, not including 0. So we're not going to run into any issues with that right here either. But these are things that we should question whenever we're dealing with functions that have domain issues, specifically with the logarithm. Okay. So let's do some more examples with exponential equations. Just one more simple example that's very similar to that one. And particularly because I want to look at a different approach to it. Okay. Last time we took the log of both sides. Now, it's a little unnecessary. I think it's better to think about taking the log of both sides with everything, because then we never really, some of the later equations it'll make a little bit simpler, but with this one in particular, we don't necessarily need to do that because the exponential functions are one-to-one functions, right? So this means that because this is a one-to-one function, this equaling this, that's just going to imply that 2x is equal to 3x plus 2. Okay, so we don't really have to take the log of both sides. We can just drop the bases immediately. And if we think about it, it should make sense, right? If we have 5 raised to some number equals 5 raised to some number, whatever that number is should be the same thing because the bases are the same thing, right? So in order for them to be equal, we need to be raising them to the same number. Okay, whenever we take 5 and we raise it to some number, we're always going to get a unique number out, right? So this is that one-to-oneness that we're invoking here. So we don't necessarily need to take log base 5 of both sides. We can actually do it a little more simply here. So this is going to be negative 2 is equal to x. And then that's it for that one. Okay, so let's look at one where there's a little bit more to it. Let's say we have 5 to the 2x equals 25 to the 3x plus 2. Now there's two ways that we can approach this problem. So let's do it both ways here. So we'll do this 2 different times. So one, again, it's both of these same ways that we just saw a minute ago. We can either take the logarithm on both sides or we can use the one-to-oneness again. So if we're going to take the logarithm of both sides, we first, of course, need to think, well, okay, what base should our log be? Because these aren't the same base, right? So we're going to do log base, we're going to want to do log base 5. I should say it's easier, I guess, if we do log base 5, but it actually doesn't matter. So maybe we can do it both ways here too, so we can see why it doesn't matter. So if we take log base 5 of both sides, okay, so I'm choosing that because that's the left-hand side of the equation's base. We're going to get 2x log base 5 of 5, which is going to be 1, equals 3x plus 2 log base 5 of 25. Now this side is not equal to 1, but it is a log that we can do by hand, right? Because we're just asking ourselves 5 to what number is equal to 25. So we can see that this one is going to be 2. Okay, so we get 2x equals 2 times 3x plus 2. So the 2 coming from the log base 5 of 25. Okay, so now it's just an ordinary equation. Go ahead and distribute, or you don't even really need to. I guess you can just divide the 2 on both sides, right, to make it a little simpler. So x equals 3x plus 2. So we have negative 2x equals 2. So x equals negative 1. Okay. So x equals negative 1. So now, like I said, let's do it a couple of different ways here. And we can see, make sure that we get the same answer. So now the next way would be, okay, what if we take the log base 25 of both sides? What if we pick the other base? Okay. So take log base 25 of both sides. Okay. So we'll still start the same way. We have 2x log base 25 of 5 equals 3x plus 2 log base 25 of 25. Okay. So now this one is equal to 1 on the right-hand side, right? Because they have the same base, same argument. So Then we just have to deal with this log over here. And this is still doable by hand because it's asking 25 to what power equals 5. So it's the square root of 25 that's equal to 5, which is going to line up with the 1/2 power. So remember, those rational exponents are the same thing as the roots, right? So this is equal to 2x times 1/2. And then that's equal to 3x plus 2. Okay. So we still, no matter which of the bases we chose here, it still leaves us with a log that we can do by hand. And you know what? I want to point out, even if we can't do it by hand, it's still fine. Like, this will still just be a number. Even if we can't evaluate it by hand, you could throw it in a calculator or something. It might give you some infinite decimal or whatever. But it's fine. It's still a number. So sometimes, if the bases aren't set up properly, that might be fine. So what base you choose ultimately really doesn't matter too much. We're picking the most convenient ones here, but even if it leaves you with something that's not, something you can evaluate by hand, you're still going to get to an answer. Okay. The right answer, I should say. So here the 2's cancel. So we have x equals 3x plus 2. So again, we're getting x equals -1. Okay, now finally, what about the third way, not even using a log? Okay, what if we want to invoke that one-to-oneness again? We can't do that right now because in order for us to invoke that one-to-oneness rule meaningfully, these need to have the same base, but they don't have the same base. But we can easily rewrite this so that they do have the same base using the exponent properties. So the left side is 5, and the right side, we could write this as 5 squared to the 3x plus 2, right? Because 25 is just equal to 5 squared. Okay. So now we can rewrite this using the power rule for exponents. We see these, we can take the product of these two. So 2 times 3x plus 2. Okay. And now because they have the same base, we can invoke the one-to-oneness, right? So this is 1-to-1. And we can say, okay, 2x equals 2 times 3x plus 2. Okay. And this was already the form we had earlier, so that should leave us 2x equals -1. Okay. So lots of different ways we can approach these problems. Similarly, like you could rewrite the 5 to the 2x part as 25 to the 1/2 power. And then they would both have the base 25, and you could use the one-to-one property there as well. So a lot of different ways we can approach these. Okay, let's do a couple that are a little bit trickier now. Okay. What if we have 3, let me write an example here. 3x plus 1 equals -2. Okay. Well, a lot like when we were doing absolute value equations, right? We knew the absolute values, they always had to be positive. Their outputs had to be positive, right? So we knew that if they were equal to a negative number, then there was no solution. And it's no different here. The exponential functions also always have to be positive, right? And they also have to be greater than 0. So this isn't going to have a solution. Okay. A way we could see that algebraically, well, a natural way for us to solve this would be take the log base 3 of both sides. So what happens when we do that? So like, just say we didn't notice that this wasn't going to have a solution. We weren't thinking about the domain or the range. So, we just take the log base 3 of both sides. What happens? Well, luckily this should stop us right here, right? We do this, on the left side is fine, but on the right side, we can't take the log of -2, right? This doesn't lead us to any answer. We can't take the log of a negative number. So right here, we can just see that there's no solution. Okay, so whichever way you do it, you should end up with no solution. Okay, let's do 5 to the x plus 2 equals 4 to the x. Okay, so this is like I was saying, there might not be a natural base for us to pick. Based on what we've seen so far, right? We're usually looking for, if they have the same base, we could take the log of that base. If they don't, then we could take the log of one of them and maybe still evaluate that log by hand. But here, 5 and 4 are not powers of each other. So it doesn't much matter which one we pick for the base. We're not going to get a just easily solvable log either way. So I'll just take log base 5, just because, no reason. You can take the log base 4 of both sides instead. You could take the log base 7 if you want, right? It ultimately should all lead to the same answer. The biggest advantage to taking the log of both sides in these is that we can get the exponent down and turn it into a product, okay? So that's the real power of the log. It's nice that some of the logs just kind of go away, but it's not necessary, right? The big advantage of these is moving the exponent down into the product. So we get x plus 2 log base 5 of 5 equals x log base 5 of 4. Okay. So the left side, we have the logarithm going away. This is just going to be x plus 2 because that's log base 5 of 5 is 1. And then on this side, we have x times log base 5 of 4. Okay. Now this is just some number. Okay. This 4 is a valid thing to take the log of. It's not a negative or zero. So you could throw this in your calculator and you would get an answer. But we don't want to do that. We just want to leave it as an exact answer. So we're just going to leave it as log base 5 of 4. So it might look a little weird, but that's okay. We can still do it. So in general, just think about this like if this was 3 or something, right? What we would do is we would get all the x's to one side. So we'll subtract x from both sides. And we get 2 equals x log base 5 of 4 minus x. Okay. So just pretending like if this was 3x, we would do 3x minus x and get 2x, right? So it's no different, even though this is a weird number, it's still just a number. So we're going to do this and we're going to get log base 5 of 4 minus 1 of x. Okay. So I'm still combining like terms here. Another way to think about it is that I factor an x out, right? Which combining like terms and factoring are really the same thing. So we're pulling an x out of here, we're pulling an x out of here. Here we're left with log base 5 of 4, here we're left with a minus 1, okay? So either way, I'm grouping the numbers together so that they're off of the variable now. So now I can divide both sides by that number. Okay. So we get x equals 2 over log base 5 of 4 minus 1. Okay. And that's our answer. It's not a nice number, but it's a number. Some books will have you take this further and simplify this a little bit more. So I'm fine with you just leaving it like this. If you want to throw it in your calculator, like if you want a decimal, that's fine too. It's all really the same. Some books, like I said, though, they'll have you simplify this a little further using that change of base formula. Okay, log of 5 minus 1. And then using your knowledge of like rational expressions to simplify this, right? So you basically multiply by log base 5 of 5 over here. So you get like 2 over log base 4 minus log base 5 over log base 5. And then you're dividing by a fraction. So this is 2 log base 5 over log base 4 minus log base 5. Okay. So, it's all the same answer. There's just kind of like a like cardinal rule in some textbooks not to leave things that can be simplified like this in the denominator. I mean, it's arguable whether this is even really more simple, right? But this is at least the right one is, or the right hand one over here is easily put into the calculator. I guess you could say at least. You could combine these two into log base 4/5, or log of 4/5, I should say, using the quotient property. So there's lots of equivalent ways to write this. You can just, you can manipulate it as much as you want. But ultimately it's all the same number. So I'm not really picky about it. So you can just leave it like this one. Okay. So I know this video is getting long, but I just want to keep all of these into one video here. So just two more I want to look at that are a little bit tricky again. 2 to the x equals 3 to the x. Okay. So how could we solve this? Well, let's go ahead and just try it. Log base 2 of 2 to the x equals log base 2 3 to the x. Okay. So we get x, and I think at this point we can just write x over here. We know this is log base 2 of 2, so it's going to be 1. Equals x log base 2 of 3. Okay. So it's starting to look a little bit strange. Namely, we're going to bring everything to one side, and then one side is going to be 0. So we have x minus x log base 2 of 3 equals 0. Okay. So this is fine though. So we get x 1 minus log base 2 of 3 equals 0. And then just like the last one, we divide by that number. This is just a number, right? So we can divide by it. And 0 divided by anything is 0, so we're going to get x equals 0, right? Okay. If we go back and look at the equation, then, it should be clear that it should have been 0 all along. We're taking 2 and 3 and we're raising them to the same number, right? X. And powers of 2 and powers of 3, they're never going to intersect with each other, right? That's just like the, if we just think about like the, how factors work, right? 2 to whatever power equaling 3 to whatever power doesn't make sense. It won't have any common factors. But it does make sense if we think about 0, because that brings them both back to 1, right? So that's like the one special number that brings them both back to the same thing. So the only way this equation can make any sense is if it is 0. Okay, and then last, but certainly not least, because it's kind of a weird one. Okay, actually there's actually two more I want to do now. This looks like I lied before. I just keep scrolling through all these equations and I keep seeing some unique ones, and I want to make sure we cover every possible case we could run into. So what about one like this? Okay, 3 plus e to the 2t equals 7 times e to the 2t. So this one's a little bit strange because, we could just take natural log of both sides, but it's a little weird because we kind of stuck on the left side, right? We can't break up addition inside of the logarithm, right? So it wouldn't really let us bring that power down. So I think a good first step is to bring all the e to the 2t's on one side. Okay, minus e to the 2t. And then we can factor out that e to the 2t or combine like terms. If you want to, I guess that would make more sense, right? This is just going to be 6e to the 2t. Again, combining like terms, factoring are the same thing. If you factor, you get 7 minus 1, which is 6. And then we divide both sides by 6. And now we can take the natural log of both sides. So we don't want to do it first because we get stuck on that addition. Okay. But now that we just have an e to the 2t by itself, we can easily take the natural log of each side here. Okay. So natural log of e to the 2t. So now natural log of 1/2, that's just a number. Over here we have 2t natural log of e, which is just 1, so we just won't write it. So we get that t is equal to natural log of 1/2 over 2. Okay. Or if you want to write it in a way that's more aesthetically pleasing, 1/2 natural log of 1/2. Right. So any way you want to write it, if you want to stick that into the calculator and get an answer, feel free. I prefer exact answers. That's just like the mathematician side of me. If you're coming more from like a computation heavy field, maybe you're more comfortable with decimals, however you want to do it. Let's go to the last one I have here now. E to the 2x minus e to the x equals 56. Okay. Very strange problem because there's no way for us to factor it now either, right? E to the 2x and e to the x are different things. We can't combine them. And there's no good way for us to break it up so that we can get an e to the x by itself like we did in the last problem. We can break up e to the 2x as e to the x times e to the x, but that doesn't really help us because even if we factored out an e to the x, we'd still be left with 2 e to the x terms. So the way we want to approach these, and this is something we might come across in a lot of different types of problems. First, we'll get everything to be 0, and then we'll make a substitution. Okay, this is going to be particularly helpful in calculus when we get into those chapters in the next class, but in some algebraic problems, it's also really helpful. So in particular, we make a substitution. We usually use the letter U as the substitution, and we call it a U substitution, but you can use whatever letter you want. It doesn't really matter. So in particular, we're going to let U equal e to the x. Okay. Now, what does that mean? That means that this becomes u squared minus u minus 56 equals 0. Okay. Why is that true? Well, u squared equals e to the x squared, which by the power rule is e to the 2x. Okay. So this e to the x, we set that equal to u, which means that this term is u squared. And why do we even want to do this? Well, now it's just a quadratic, right? And we studied quadratics a lot. We have factoring techniques for this. We can solve quadratics. You can throw any quadratic at us and there's a way to solve it. If everything else fails, you can just use a quadratic formula. So we get u minus 8, u plus 7 equals 0, right? So that means that u is equal to 8 or u is equal to minus 7. And we're not interested in what u is, we're interested in what x is. So we make our substitution again. Now that we have an equation with, if we just have u equal to something, now we can make that substitution again and get e to the x equals 8 or e to the x equals negative 7. Okay. Now this one doesn't make any sense because e to the x can't be a negative number. Its range is 0 to infinity. But we can take the natural log of both sides over here, or you could just use the inverse log property if you want to think about it that way. However you think about it, you're going to get x equals natural log of 8. And that's it, right? I mean, that's our answer. Natural log of 8 is just a number. So to recap, how do we know to do this? Well, we can think, this kind of looks like a quadratic, meaning that we have one term is the square of the other term, right? And there's no other way for us to do anything, right? We can't get e to the x by itself otherwise. So we go ahead and make a substitution, and we make it look like a quadratic. And you can technically do this without the substitution. The substitution just makes it easier to see. But I mean, you could just factor this as e to the x minus 8 times e to the x plus 7. It's just, we don't normally study problems like that. So it's a little weirder. But the substitution just kind of, it just helps us relate it back to the polynomials, right? But yeah, so we make the substitution, we use our old techniques for factoring, and then we do the substitution again.